Okay. Hello everyone. Today I'm going to present my work on the final project, named unsupervised and supervised learning of handwritten digit recognition using the MNIST database. So my presentation will be divided into 5 sections: introduction, data, methods, results, and conclusion and discussion. So the subject of my research for this final project is predicting handwritten digit. So this is a class multi-class classification problem. So the MNIST database is often used to train models for predicting or recognizing the handwritten digits from 0 to 9. And the test set accuracy, prediction accuracy can be as high as 98% using deep neural networks. And the the primary objective of this project uh, is to apply the supervised learning method learned in this class to this classical problem, and to compare the performance of this classification method to deep neural networks. And the secondary objective is to explore the latent structure of the MNIST data using supervised learning method, such as non-negative matrix factorization and the k-means clusterings. So the full name of this MINIST data is called Modified National Institute of Standards and Technology. So it consists of 6,000 training images and 10,000 testing images of handwritten digits from 0 to 9. And each image is represented as a 228 by 28 grid of grayscale pixels. And the following picture is examples of those images. So so the response variable for this final project is handwritten digits from 0 to 9. So this is of 10 classes. So that's a typo. That's not a binary. It's a 10 class response variable. And we have 28 times 28, equal to 784 predictors. And each predictor takes on a integer value ranging from 0 to 255. And the 0 corresponds to completely black pixel. And 255 correspond to a complete white pixel. And the values in between 0 and 255 represent varying intensity of gray, the color gray. And for the supervised learning method, we apply the following 6 classification methods: multinomial, logist regression, decision tree, which is a single tree, and k nearest neighbor KNN, and a random forest, boosting trees, and a support factor machine. So the main challenge of this data analysis is the computation burden of hyperparameter tuning and model training caused by a large number of predictors. So my solution are as follows. So I used the 5-fold cross-validation to tune the hyperparameters. And I only performed the hyperparameter tuning on a subsample of the training set to alleviate its computation burden. And I did a parallel computation for boosting trees. And I attempted to use a dimension reduction method, principal component analysis to reduce the number of predictors. But in the end, due to interpretability, I didn't include the result. So 67 predictors exhibited a zero variance in the training set, means they are sparse variable predictors. All the values are equal to 0. So the standardization was performed within each CV cross-validation split. Predictors were standardized using means and standard deviations computed from the training portion, i.e. the 4 training folds. And this summary statistic was then applied to the corresponding validation fold. And after determining the optimum values of the hyperparameters, predictors were re-standardized using the summary statistic computed from the full training set. And the same standardization was applied to the test set to prevent information leakage. So for the unsupervised learning part, we performed the non-negative matrix factorization on a random subsample of 2,000 images from the training set to explore the latent patterns of those 2,000 images. So in particular, specifically, NMF approximated a non-negative image matrix as a matrix X approximately equal to the matrix multiplication of W and H. So the rows of W provided the low dimension representation of the sampled images in terms of the 10 NMF components. We then applied the k-means clustering to the rows of W. So we set k equal to 10 to match the number of digits. So finally, we compared the resulting k-means cluster with the true digit labels. So the package used are listed here. So tidyverse for data manipulation, caret for k-nearest neighbor, tree for classification tree, random forest for random forests, and GBM for boosting trees, and E1071 for SVM, and do parallel for the parallel computing when we implement the boosting trees. And NMF, non-negative matrix factorization for non-negative matrix factorization. So here's the results and the tuning hyperparameter tuning result and the test set performance on the test set performance. So we can see that the boosting trees achieved the highest achieves the best performance, predictive performance amongst the all the methods considered, and followed by the random forests with a test error of 0.045. So the prediction accuracy for these two methods were around 96%. So and KNN and the SVM also performed well with similar test errors of around 0.05. And the multinomial logistic regression had a higher test error of 0.0831, and but still achieved a reasonably good predictive performance. In contrast, the classification tree performed substantially worse than the other method. So the test error of the classification tree nearly 10 times larger than that of the boosting tree. And the following are the results of NMF dimension reduction and the k-means clusterings. So the class labels were arbitrarily assigned by the k-means clustering and did not correspond to did not correspond to the true digit labels, and the dominant true digit was the most common true digit label within each cluster, and the cluster purity was computed as the ratio of the number of the dominant digit and with the cluster size. And as we can, I calculated the overall class purity, which was 55.8%. And as we can see that a couple from the table, a couple of cluster showed a strong correspondence with single digits. So they are cluster 4 for digit 0 with a class purity of almost 90%. And also class 6 for digit 2 with a class digit of over 90%, 92.2%. However, most clusters contains a mixture of multiple true digit labels. So this suggests that the NMF representation did not perfectly separate all digit classes, but it did capture some meaningful digit structures, i.e. strokes, as shown also in figure 1. So as we can see from this figure, component 2 captured the oval shape of digit 0. And the other components capture the horizontal and slightly tilted strokes common in digits such as 1 and 7. So the conclusion for this data analysis work is are that for this project, ensemble method were the most effective in predicting handwritten digits. This is also suggested by theory because when we combine several weak learners such as a single tree, it will improve a prediction performance substantially. And boosting tree achieved a comparable predictive performance around 96% prediction accuracy to the deep neural networks with the following settings. So 500 node hidden layers, rectified linear unit activation functions, and a stochastic gradient descent optimization with a learning rate of 0.01. So as we already discussed, a couple clusters showed strong correspondence with a single digit, but most cluster contain mixture of multiple true digit labels, and the NMF representation did not perfectly separate all digit classes, but it did capture some meaningful digit structures as shown in figure 1. And these my references. And thank you for your attention to my presentation. Thank you.